Let's move on to the other concept of retrosynthesis, that is one group CX disconnection. What this states, one group CX disconnection? Any idea? So one group CX disconnection, here you will be having one of this CX bond which is present in the target molecule, and you are planning to disconnect this CX. So we disconnect a bond. So in this case, first carbon and X can be of any carbon, oxygen, nitrogen, and sulfur. So X is usually stands for heteroatom. We disconnect the bond joining the heteroatom, that is X, to the rest of the molecule where CO, CN, CS disconnection exists. The corresponding reaction are mostly ionic, involving nucleophilic displacement by SN1, SN2, or carbonyl substitution with amine alcohol thiols on carbon electrophiles. So during this disconnection, generally you will get the ionic symptoms, and generally how to recombine, you need to use with either SN1, SN2, or carbonyl substitution with amine alcohol thiols on the electrophilic carbon. The normal polarity of the disconnection in one. So as and when you have this kind of target molecule Rx, R can be alkyl, then X. So this also comes under this one group CX. So there is an one group of CX is present in this particular molecule. Then the reaction disconnection site in this Rx molecule, target molecule, is between the R and X bond. So during the disconnection, that is CX disconnection, you will get the two types of syntons. One is R plus X minus. So R plus and X minus will act as the syntons. Then corresponding synthetic equivalent or reagents, as and when you have an R plus, then RHAL plus X minus. X minus is synton, can be converted into synthetic equivalent of HX. So these two reagents are available. The normal polarity of disconnection of one will be cationic carbon. This is the cationic carbon synthon, and anionic heteroatom synthon. So always this X minus prefers to carry some negative charge, represented by acyl or alkyl halide 4. So you can propose the reagent of acyl or alkyl halide 4 as electrophiles, and amine alcohol or thiol 5 as a nucleophile. So you can HX can be, you can propose this amine alcohol or thiol as a nucleophile for this. So then only you can reconstruct this target molecule. The one group CX disconnection. So the synthesis of ethers, in this case, how to do the disconnection with respect to one group CX disconnection. The question of which bond needs to be disconnected in this particular target molecule can be much more significant in the synthesis of ether. So you have a ether linkage here, the CH2O and CH2O. So this will also act as a CX, and this will also act as a CX bond. Now there is only one group is available, that is CX group is only one group is available over the target molecule. Now this in this case X is O. Which bond to disconnect can much more significant in the synthesis of ether? While synthesizing this, which if you do the disconnection, you will get the suitable synthetic equivalent. So whether do we need to follow path A or path B? Because there are, this is CH2O, that is CO and CO bond is available. And suppose if you are following the disconnection in this fashion, that is path A, the synthetic equivalent will be PHCH2Cl, because the synthon formed will be PHCH2 plus some, and the synthetic equivalent will be PHCH2Cl. And on the other hand, O minus will be the synthon, and the protonation of O minus will resultant in the formation of alcohol. Instead of following path A, suppose if you are following the path B, then path B synthetic equivalents are first cleave it here and you will get PHCH2 O minus, that is synthon, and the protonation of synthon will resultant in the PHCH2 OH plus. On the other hand, you will get CH2 plus plus is a synthon, and if you have a CH2 plus, then you can do the Cl minus or Br minus as in Br minus, then you will get this product 5. So reactant can be of this C, CH2, CH2, then Cl. Now, which reaction needs to be used? Reactants needs to be used in order to reconstruct this target molecule. So, with many ether, like gardenia perfume, this gardenia perfume, this is the target molecule, gardenia perfume, the compound one. The gardenia perfume structure is this one. And in this case, you have a many ether linkage like CO. There are just two CO is available for the disconnection. It does not matter much, but you need to be very cautious which is the site of disconnection. Starting material will be an alcohol 3 or 4. There are two alcohols, right? So alcohol 3 obtained if you follow the path A. Alcohol B, there is some alcohol 4 will be obtained if you follow the path B. Now you need to consider certain aspects and you need to design the synthetic protocol in such a way that you need to get this target molecule during the synthesis. The starting material will be an alcohol 3 or 4, or else you may have the alkyl halide 2 and or 5. So if you path A product, path A will generate this starting material alkyl halide. Path B will generate this alkyl halide. The reaction will be carried out by treating the alcohol with base strong to form anion. Generally, sodium hydride is the favorite as the hydride ion is extremely hard and act only as a base, never as a nucleophile. That's why you can preferably use NaH, sodium hydride. Sodium hydride will act as a strong base. It won't act as a nucleophile. The either chloride is available. So there are two chlorides are available. Both react in SN2 reaction. Both will proceed via SN2 reaction. SN2 reaction means whether it is two-step, single step.
One step SN2.
SN2 is single step reaction, and reaction intermediate is formation of transition state, right? Okay, so the chloride is available. Both reactant react in SN2 reaction. We prefer route A. So route A as benzyl chloride 2 is more reactive and cannot undergo elimination while 5 just might. So in this case, you need to prefer this particular as a reaction reagents, not this path B. So why? Both will prefer to undergo via SN2 mechanism in order to get this target molecule. But there is a slight possibility in path B that it may undergo elimination reaction. So elimination reaction means formation of olefin, right? So if you are using a strong base, then what will happen? The deprotonation from the more acidic site, generation of carbon ion, this carbon ion shift over here, and it may push this Cl as a Cl minus. Resultant will be, you will get double bond. So elimination reaction is possible if you are using this as one of the reagent and taking this as another reagent. But if you look into this, in this case, This OH is acidic over this particular carbon carrying the hydrogen. If we're using this NaH, then H minus will deprotonate it. The resultant will be H minus formation. H minus formed will act as a nucleophile, prefers to attack over the benzylic carbon, which is carrying the leaving group, and this will knocks out as a Cl minus. Resultant will be formation of target molecule. That's why you used to prefer the path A is the right path, not the path B. Because if you follow the path B, you may get some conversion of target molecule, but along with that, there is a side reaction, that is formation of eliminated product. Okay, so in this case, take the 3 as a starting material during the synthesis, then use the base, then oxyanion formation, formed oxyanion, then you need to introduce the corresponding benzyl chloride, that is 2, then nucleophile attack over the carbon carrying the leaving group, transition state formation, then target molecule formation, that is gardenia perfume. Similarly, in connection with the synthesis, one group CX disconnection, the synthesis of sulfides can also be an example. Unsymmetrical sulfide. So this is an unsymmetrical sulfide. Unsymmetrical means the R dash and R2 dash are different. R1 and R2 are different, which present over this sulfide. That's why unsymmetrical sulfide 1 need the same disconnection we have just used for ether. The anion 3 of thiol 4, anion 3 of the thiol 4 will combine with the alkyl halide 2 to make the new CS bond. The reaction is much easier with the sulfur. Thiols are more nucleophilic towards saturated carbon than alkoxides, and the risk of elimination is much less in this case. So the reaction is much easier with the sulfur. Thiols are more nucleophilic towards the saturated carbon than or alkoxides if you compare with the alkoxides. So in this case, usually nucleophilic characters are saturated over the saturated carbon. The risk of elimination is much less in this case. Suppose if you're having this kind of unsymmetrical sulfide, then first do the disconnection, CS disconnection, then R dash halogen 2 plus along with that S minus R2. This is the 3. So follows further disconnection, where usually you will end up with the thiol R2SH. So another example is acaricide that kill mice and ticks, the chlorobenicide. This is the structure of the chlorobenicide. This also has some carbon and sulfur or carbon and X bond disconnected to give an acidic thiophenol. So thiophenol you will get it 6 and reactive alkyl halide 7. The synthesis merely combine these two in ethanol with sodium ethoxide as a base. So the reaction condition is ethanol and sodium ethoxide as a base. Then you can reconstruct this target molecule. So during the disconnection, try to do the carbon sulfur cleavage, not over this carbon sulfur, because it will leads to the complicated reactant. Instead, you always think about that the CH2S, if it is available, try to do the disconnection at the CH2S site, because you know that this thiol is the S carries a negative charge and SH is the synthetic equivalent for this S minus synthol, and the CH2 plus, as and when you have a CH2 plus as a synthol, then you can propose the CH2Cl as a synthetic equivalent. Choosing a choosing a route mechanistically, so you need to be wise while preparing the disconnection site. In other cases, the choice can be made because only one of the two SN2 reactions will work well. The allyl phenyl ether. So allyl phenyl ether, this is the target molecule, allyl phenyl ether. In this case, there are two sites is available for the disconnection of CO and CO. So path B and path A, you can propose it. The path B will leads to the formation of two synthetic equivalents or reagents. The path B will result in the formation of phenol as one of the reagent and 34, that is allylic bromide. Allylic bromide and phenol. Suppose if you are following the path A, then path A will result in the bromobenzene, that is bromobenzene 30, this is the bromobenzene structure. Then allylic alcohol, 31, allylic alcohol. So if you follow the path A, you will get allylic alcohol and bromobenzene. Instead of following the path A, if you are following the path B, then phenol and allylic bromide. But you have these